Welcome back to the deep dive. So today we're starting with a concept that seems, well, pretty straightforward, something you probably learned way back in science class. Physical work.
Yeah, the classic definition, right? Work is just force applied over a distance. Simple.
Simple, elegant, and, well, according to the material we're looking at today, maybe fundamentally broken when you really examine it.
The contradiction hits you almost immediately. The classical view hinges completely on motion. So if nothing moves, no displacement, then technically no work is done.
But, and this is where it gets tricky, you, the listener, know perfectly well that just holding something heavy, say, a 50-pound weight steady over your head, takes a huge amount of effort. It's exhausting. You're definitely burning energy.
A lot of energy. And that effort, that energy cost, just to stay still, to maintain stability, that's the paradox we're diving into today.
Exactly. Our source material, specifically Part 6 of the Graviton Pressure Theory or GPT framework from Sharif Ali Rashada, argues this isn't just some minor exception. It's presented as a core logical failure in classical mechanics.
Right. So our mission really is to unpack why that traditional formula kind of falls apart under scrutiny and how this GPT framework offers a different definition, one that's meant to be, empirically consistent.
And before we get into the weeds, maybe a quick word on GPT itself.
Good point. Yeah, so GPT in this context isn't about language models. It's a framework that looks at gravity differently. Instead of just space-time curvature, it posits gravity as an actual physical pressure field, like a background pressure everywhere.
Okay, a pressure field.
Yeah, and objects have to constantly resist this pressure to just maintain their shape, their coherence. It's framed very much as an engineering approach, trying to solve these kinds of energy accounting puzzles.
Got it. So GPT redefines work to include the energy needed for active resistance, for stability, not just for causing movement. Let's tackle that main conflict head on then. Classical, no movement, no work, reality. Systems burn energy to stay still. This source material argues the classical definition just collapses pretty fast with real-world examples. The one that really stood out to me was the robotic arm.
Oh, yeah, that's a great illustration. So picture this advanced robotic arm, right? It's holding a heavy weight, maybe 10 kilograms, completely still, fully stretched out.
Okay, perfectly stationary.
Perfectly stationary. Gravity's pulling down, the arm's pushing up. Stasis, so classically, displacement is zero. Work done.
Zero, according to the formula.
Zero. But what's actually happening?
Well, the motors are running, right? There's got to be power going to it. Batteries draining.
Exactly. Significant electrical energy is being used continuously. The motors are actively generating force, very precisely, just to counteract gravity.
And the key point, I think, was cut the power.
Instantly, the arm drops. Bang.
Right.
And the fact that stability is lost immediately when the energy stops.
Right.
That proves the energy was being used for something crucial, right? For the physical task of keeping it there.
It wasn't just leaking out somehow.
No. If that static state truly involved zero work, cutting the power wouldn't matter. And this isn't just about fancy robots.
You mentioned bridges earlier, these massive structures.
Yeah, think about a huge bridge. It holds its shape because of constant internal forces. You've got tension in the steel cables, compression in the concrete pillars, all actively fighting gravity's pull day in, day out.
But again, the bridge itself isn't moving across the river, so classical physics says.
Zero work done by those structural forces. It dismisses them in the work calculation because the overall displacement is nil.
But hang on, materials fatigue over time, don't they? You get crude, tiny cracks. Things need constant inspection and maintenance. Doesn't that degradation suggest there's some ongoing energy exchange, even if we can't see the bridge moving?
Absolutely it does. That's a key piece of evidence. The fact that materials wear out under constant load proves it's not a passive state. It's dynamic. It's active resistance. Think about magnets, too. A strong magnet holding, say, an iron block against gravity. Classically. Zero work. But there's obviously an active force counteracting gravity. There's tension within the atomic fields making that happen.
So the fundamental issue, the logical collapse as the source calls it, is that classical mechanics seems to only value visible movement. It mixes up measurable displacement with meaningful effort, maybe. It denies that actively resisting, just staying put, costs energy and is effort.
That's the core argument, yes. It ignores the energetic cost of stability.
Okay, so when classical physicists face this, like with the robot arm, what's the usual counter-argument? I think the source mentioned they try to explain it away.
Yeah, the common way to try and save classical definition is to say, oh, that energy the robot arm is using, that's just inefficiency. It's heat loss in the motors, electrical resistance, friction. It's waste, not real work being done on the weight.
So it's just messy reality getting in the way of the clean equation.
Exactly. But that's where the GPT framework really pushes back hard. It argues that calling that energy consumption mere loss or inefficiency completely misses the point. It ignores the purpose of that energy.
The purpose being to not fall down.
Pretty much. To maintain that specific position, that structural arrangement against gravity, we need a better way to distinguish between, say, actual heat waste and purposeful energetic effort that results in stability.
Can you give an example of that distinction, true loss versus purposeful static effort?
Okay, let's take a simpler case. Imagine a really strong spring holding a heavy vault door shut. That spring is under constant tension, right? Exerting force constantly.
Right.
If that door stays shut for a year, classical work is zero. Now, if it's a near-perfect spring system, maybe very little heat loss, very little friction, the spring itself is still stressed.
Yeah.
It's actively maintaining that tension against whatever force is trying to open the door. That sustained tension is the purposeful effort. True loss would be like if the hinges were incredibly rusty and generating a ton of heat only when the door was actually swinging open or closed. The energy spent just holding position isn't lost in the same way.
That makes sense. So for the robot arm, the electricity isn't just making things hot, well, maybe some of it is, but its main job is providing the energy to keep the arm's structure organized, its coherence against gravity pulling the weight down.
Precisely. And if you just label all that energy consumption as loss, you're basically denying its absolutely essential role in preventing the weight from dropping. You're ignoring the cause and effect.
It's active structural maintenance, as the source puts it.
Yes. And we see evidence for this. If you use sensitive instruments to measure the strain inside materials under constant load, like in a bridge beam.
You mentioned micro movements before.
Right. We see things like elastic deformation, creep, viscoelasticity. It's not truly static at the microscopic level. The material is constantly shifting, absorbing energy, redistributing stress, all to maintain its overall shape.
So the eventual fatigue, the wearing out, isn't just random decay. It's proof that maintaining stability is an active, ongoing process that uses up the material's integrity over time.
Exactly. It's not passive equilibrium. It requires continuous energetic input or management.
Okay, so the consequence of just calling this inefficiency isn't just about words. It leads to bad accounting, right? If you ignore the energy needed just to hold things together against gravity.
Your energy budgets are wrong. Your engineering assumptions might be flawed, especially for long-term structures. The system might eventually fail, not because of some unexpected flaw, but because the constant necessary work of resisting gravity was never properly accounted for as work in the first place.
All right, so if calling it loss doesn't work, we need the solution proposed by GPT. Classical work is about causing movement. GPT needs to include resisting movement.
Exactly. GPT tries to resolve this by basically saying both are physically real work. The definition shifts. It's less about displacement dollars and more about coherence.
Coherence maintenance. Okay, so work becomes, say that again, the energetic cost
of maintaining or reconfiguring coherence within this background graviton pressure field.
Maintaining or reconfiguring. Okay, so how does GPT actually quantify this, especially when the big D, the displacement, looks like zero?
This is where they introduce a new idea, conceptually at least. It's called coherence. It represents the internal effort. Stability, in the GPT view, isn't passive. It's an active, continuous energetic effort to hold the structures formed together against external pressure.
Okay, to a coherence. You described it as the internal structural adjustment needed, even microscopically. Can you maybe give us a picture of what that looks like?
Let's try that Jenga analogy from the source. Think of a steel beam under heavy load, not as one solid thing, but like a microscopic Jenga tower.
Okay, tiny blocks.
Tiny blocks. And this pervasive gravitational pressure field is constantly trying to nudge those blocks out of place, just slightly deform the structure.
Yeah.
That's kind of what leads to creep and long-term deformation.
Right.
Coherence is trying to model the sum of all those tiny internal micro displacements that the system has to constantly correct. It needs energy, either from the material's own atomic bonds or, in the robot's case, from the motors, to keep pushing those tiny blocks back into alignment to resist that constant pressure and stabilize the overall shape.
Okay. So it's like the system is constantly doing tiny bits of work internally to undo the nudging from the pressure field, even if the whole thing looks still from the outside.
That's the idea. It's the constant microscopic reversal. of potential gravitational deformation.
That analogy really helps clarify it. So visible displacement might be zero, but internally there's this dynamic adjustment happening all the time.
And GPT says that internal structural management, that's the work being done. It's performed by the structure's organization itself. And this way, you can account for the energy being consumed by the robot arm, for example.
It becomes meaningful structural work.
Yes. It connects the energy input directly to maintaining the state of stability.
Okay, I see the logic, but let me push back slightly here. If work is happening constantly inside almost everything just to hold its shape, does that mean everything is always doing work? Does the definition become too broad, almost meaningless? Like, is this table doing work right now?
That's a really important clarifying question. GPT is specific here. It's about maintaining coherence against an external pressure field when the system is in a state of non-equilibrium.
Okay, unpack non-equilibrium.
Think of a rock just sitting flat on the ground. It's pretty close to its lowest energy state relative to gravity locally. It's in a kind of passive equilibrium. It doesn't need much active input to stay there. But the bridge, or the robot arm holding that heavy weight, they are in active, high-energy non-equilibrium states.
Meaning they would collapse or fall if not for continuous effort.
Precisely. They require constant energy input or internal stress management to prevent them from decaying to a lower energy state like collapse or just resting on the ground. So the work is specifically the effort required to maintain that unstable high-energy configuration against the constant gravitational pressure trying to break it down.
Okay, that focus on required maintenance against pressure provides the necessary boundary. It's not just any stability, it's stability under duress, stability in a high-stress state.
Right. It keeps the definition tied to a measurable energy requirement and a specific cause resisting the pressure field.
That makes sense. So this redefined work provides a different causal story. What about proving it? What are the practical, maybe measurable ways this GPT definition lines up better with reality than the old one?
Well, the framework leads to some specific testable predictions. Let's go back to the robot arm.
Okay.
Classical physics pretty much ignores the energy used when it's holding still.
Yep.
GPT, however, predicts that the energy consumed should scale predictably with how much resistance is needed.
So, like if the arm has to hold twice the weight or hold it further out where the leverage is greater?
It should consume proportionally more energy just to stay stable. And the claim is that experiments confirm this. The energy needed for static holding isn't just random noise. It follows predictable rules based on the load and configuration.
That's a concrete prediction.
Yeah.
What about the bridge example?
In structural engineering, there are sophisticated techniques now using sensors, strain gauges to monitor what's happening inside materials under load on a microscale.
Right, you mentioned seeing the micro movements.
Exactly. And those tests apparently show this continuous energy redistribution, this constant internal adjustment within the material. It fits the picture of active coherence work, not a passive state.
Okay. And the magnets, you said that was a strong point.
Yeah, the argument is that sensitive measurements can detect ongoing energy exchanges at the atomic level in a magnet object system that's fighting gravity. It's not just a static force field, it's an active energetic interaction needed to maintain that magnetic bond against the gravitational pressure.
It's interesting how this reframing touches so many areas. It's not just mechanics. The source mentions aerospace.
Right. The structural integrity of an aircraft wing, for example. It has to constantly maintain its shape against both aerodynamic forces and gravity. GPT would frame that as continuous active coherence work being performed by the wing structure itself.
And even quantum mechanics, that seems like a big leap.
It is, but the hypothesis extends there too. The idea is that maintaining quantum coherence, keeping a quantum system in a stable, specific state, which is crucial for quantum computing, for instance, might also be a form of active energetic work against destabilizing influences or fields.
So preventing decoherence requires energy.
That's the suggestion. And apparently, some experiments looking into the energy costs of maintaining quantum states are starting to align with this view that coherence isn't free. It requires active energetic input.
Wow. Okay, so wrapping this up, GPT seems to force a pretty fundamental shift in how we think about stability. It's not the default passive state anymore.
No, it becomes an active process, something that requires continuous energy, continuous management, continuous work in this redefined sense.
And the new definition aims to create a more consistent link between effort, whether it's causing motion or resisting it, and the actual flow and cost of energy in maintaining structures in the universe.
That's the goal, yes.
Yeah.
A unified causal framework.
So to leave our listener with something to chew on, If we accept this idea, if every stable structure around us, from a tiny component to a massive skyscraper, and maybe even down to the atomic level, is constantly performing active work just to hold itself together against this background pressure, what does that really change about how we should think about, well, everything? Specifically thinking about human infrastructure, buildings, bridges, roads, if stability itself requires continuous work.
It poses a provocative question, doesn't it? How should we then design, build, and maybe most importantly, account for the true long-term energy cost of just maintaining the things we build? Is all the maintenance we do just topping up the energy needed for that ongoing structural coherence work against pressure?
A fascinating thought to end on. Thanks for walking us through that complex idea.
My pleasure. It certainly gives you a different perspective on just standing still.